I think we will switch to Q&A session. All right. Maybe we can switch to a question for Adrien. The question is from Thomas Sauder. And he asks, Adrien, did you manage to validate the acceleration spectrum prediction with in situ data with a buoy plus measured accelerations?
Yeah, so our deep learning approach for the prediction of acceleration was based on synthetic data. So the first step was to validate the prediction based on the numerical model output from OpenFast. And then we tried to validate the prediction also with the data measured thanks to the acceleration. But we faced a problem is that was in fact due to the numerical model that we used to create the database. So we used the first version of OpenFast where we didn't calibrate the modes of the structure based on the studies that Jérôme and César presented at the beginning of the webinar. So in fact, when we compared the prediction of the deep learning approach with the in situ data, we found the mismatch that César highlighted during the presentation. But if we compare the prediction of the deep learning with the numerical model based on OpenFast, we have a good prediction. And the only mismatch between the in situ and the prediction from the deep learning was due to the calibration of the numerical model that we used to create the database for the training phase. So the next step will be to create a new database with the new calibrated OpenFast model as presented César, and to weight our deep learning architecture with this new synthetic data obtained thanks to the numerical model of OpenFast.
So first one from Owen Pocock. Were any physical sensors, monitors placed on the mooring lines? If not, did you calibrate the digital twin response for the mooring lines? So on this, I can try to answer for both Zephyros and Demosat. For Zephyros, we didn't have very precise measurements from the mooring line ends, neither anchor positions, and so we did calibrate the length of the mooring lines to match the surge and sway frequency, natural frequency of the system. And for Cytec Demosat, well, I guess they perform more or less the same exercise, but we got the model from Cytec, so maybe Manuel is the one to answer this one.
Yeah, Roman. We installed load pins in each mooring line of Demosat, but after installation we have a problem and we start to receive odd values. That it was like a constant value in each line, and we have not been able to repair that sensors. But we have validated our numerical models with the offset from Demosat and the one of the numerical model that we have in SIMA, and we have a good correlation in the offset.
Yeah, actually this situation is quite common for floating offshore wind, and that's why also it's interesting to get a model running to replace sensors when they are not working. and she asks about mooring line stiffness. Could differences in mooring line stiffnesses measured versus theoretical influence the dynamic, rigid body, tower eigen mode of the floating offshore wind turbine? Are you able to verify this? Well, I will say that depends. About mooring line stiffness, if we look at the mooring system stiffness as a whole, yeah, for sure, it will influence the dynamic of the model, and it will influence the rigid body modes. Yeah, that's how we did calibrate actually the Zephyros model. For the tower eigen modes, we do not observe a lot of variation of those modes with the sea states. So this could indicate if there is any influence. It may be low, but we did not really investigate that deeply. So I hope we answer these questions. And on another project, which is called Mon Amour, and now BAMO's project is running for in France Énergie Marine, we have a very close look at polyamide mooring lines and how you can model the dynamic stiffness of such mooring lines thanks to subsea sensors. And also we try to model the behavior of the rope with models to be able to replace those sensors when they are not available or broken. So Jean-Noël Tori asked, well, to Romain, the process described here is mainly physics-based, measured environment applied to ArcFX-like software. Yes, I agree. Do you consider developing digital twin that assimilate motions or other sensors data? Something like meteor model, data assimilation, Kalman filter, etc. Yes. Well, there is an interesting thing with physics-based model is that you can discuss with and give feedbacks to design teams. At least it's more easy to do so when you use the physics-based model. What we observe as well is that despite some anomalies, those models have satisfying accuracies. However, you can use data assimilation. You can use other type of more data-driven model to compute other models which are a bit decoupled of the simulation one. And you will have the major interest of doing so is that it can be very quick to run. Well, today we observe that we have with limited resources, we can run the simulation model, and then Adrien showed you that we can also do like surrogate model to derive acceleration or whatever sensors from other sensors like environmental sensors. or other sensors from structural point of view. Well, to our perspective, honestly, the most interesting way of looking at it is to use specific tools to detect anomalies in the data itself, rather than trying to make regression. I don't know if it's shared by Adrien also, which was involved in such work, but yeah, the anomaly detections there, deep learning, data simulation, model-driven, data-driven model. I think they have a lot to do in the field. Sorry for being a bit long there. Okay, a question from Théo Gentil to Manuel. Manuel, from a project owner point of view, what are for you the best income insights that you are expecting to retrieve from such a digital twin model?
Hi. First of all, that we can run a lot of simulations, as it is an automatic process, and then the tool that they have that Fransen Energy Marines has developed, that is very useful for post-process all this data. And we also can use it for calibrate our numerical models in a more quicker way, and also predict some behaviors of the platforms that, for instance, we are not having. For instance, we have run simulations with significant width heights of 8 meters, 9 meters, and at least at the moment we don't have that sea state in demos, well, in BMAP.
Yeah, actually, I think we can say it is that we will pursue the work with SciTech and RWE on this subject in the coming months. So it's a start. Here we only have a few sensor channels and a limited data set, especially in terms of productions from the turbine, and we will have a deeper look at all these data. Okay, we had questions from Nicolas Germain. Hi, Nicolas, by the way. I think it is for Adrien. What are the faults anomaly monitored with the sensors in the work? So yeah, I think it is related to the presentation, Adrien. Maybe you can give insights.
Yeah, so it depends of the supervision, supervised or classification or unsupervised classification. So I presented the unsupervised classification. So we use only the acceleration from the S-morpho sensors. So the idea was, in fact, to detect the operational state from the acceleration, because we only had access to 1 month of SCADA, but we are still recording the acceleration. And the idea was to use the acceleration to see if the wind turbine is operating or not. So this was the idea of using the autoencoder to detect such operational state. So it was for the unsupervised classification. And for the supervised classification that I didn't show the results during the presentation, but the idea was to perform synthetic anomalies. So, for example, we performed mooring default. So we moved the onshore and see the response thanks to the numerical model of OpenFast. And we also performed like a gearbox default. And then we used the logistic regression to perform classification on on specific quantity of interest, and we were able to classify the anomalies. So, for example, gearbox default based on the response of the system using the logistic regression. So it really depends. But in terms of sensors, we only had the possibility to detect the operational states due to the fact that we only had access to in situ data of the accelerations obtained through the S-morpho sensors. But then using the open-fast numerical model, we are able to do synthetic anomalies and then use a machine learning algorithm to perform classification. I hope to answer your question.
Are you able to compare the rainflow counting on marine lines in the numerical model and real pin load datasets? Well, so I think it's about this graph. And the answer is unfortunately not. Well, Manuel explained that marine line sensors did not work as expected. So yeah, it was not possible neither in Demosat. In Zephyros, it is the same status. So for sure, it's a bit frustrating. However, I mean, to perform tension rainflow counting, we can still have an idea of the accuracy of the model by looking at the natural frequency periods of the system, which are not perfect, but in the good in the good order of magnitudes. Well, unfortunately, here we don't have surge and sway, which are the most sensitive to the mooring system. So yeah, we will look at it later on in the project. And yeah, anyway, in a farm perspective, we don't expect every wind turbines will have some load pins, but for sure it would be interesting to compare this from at-sea measurements. Well, on other applications, it was already checked that when you have good natural frequencies, you are not too far on the modeling of the mooring lines. And yeah, okay. So for sure, when you switch from sensor to model, you at some points you need to have checking points to ensure that you can trust your model. Well, that's the difficulty here.